In the block of modeling, we have spoken about the ordinary differential equations of the plant model or the process models. We could see that there are linear ordinary differential equations for the linear problems, and there are nonlinear ordinary differential equations for the nonlinear problems. I have presented you two very simple linear problems. It was a vehicle, and I presented you a very simple nonlinear model, which is the liquid level control system. Now I would like to go back for that results, and the result is usually an ordinary differential equation. In these lectures, we are going to speak about linear and time invariant systems. So if we are lucky, our model is linear. If we are not, our model will be nonlinear, but many of the nonlinear problems can be linearized by the presented linearization technique. So there are mainly two problems, the MIMO systems with multiple input and multiple output, and the SISO or the single input, single output system. In this lecture series, mainly we are going to focus on the second one, which has got only one input and one output. In this representation, u is u of t, so it's a time function for the input. It's a scalar time function, and there is one output y of t. The state vector is called x, is denoted by x. So x is the state vector. The first equation is x dot, so we need the time derivative of x, the time derivative of the state vector, which is equal to ax plus bu. A is a matrix which has got n row and n column, as I presented it here with the details. So it's a quadratic matrix, n by n matrix. B is a column vector with n elements. Of course, for the MIMO systems, the capital B has more than one columns, so it's only the difference. The second equation is for the output y. Y is equal to C transpose x plus du, and as it can be seen, this equation doesn't contain any time derivative, so it's just an algebraic equation. And C transpose is a row vector with one row and n elements. Of course, for MIMO systems, it's also a matrix with not only one but more rows. And D is a scalar value for the SISO systems. For SISO systems, D is sometimes supposed to be 0. And at the second part of the controller synthesis block, we are going to start with the models in which D is equal to 0. So we will suppose that D is equal to 0. Of course, it's valid for the MIMO systems too. So the state space representation of a system contains n differential equations. So I put it here, n, because the number of the states is n. We have solved one problem in which n was equal to 1, and we presented another one problem, the second vehicle problem. In that case, n is equal to 2. So the number of the states is usually n. It is coming from the dynamic parts of the system. And the state space representation contains only one algebraic equation for the output. So how to solve this system? As I mentioned you before, we are going to use the Laplace transform to solve this by hand. But by software, usually we have to solve numerically by a software tool the first equation x dot. And from this x dot, using the initial condition, we will have the functions for the x. So we will have some n time functions. And if we know x, we can use the algebraic equation here, y is equal to c transpose x plus du, with which we can calculate the output function 2 numerically. So we are going to get a graph. So for the solution by hand and by using time domain techniques, we are not going to work on. But for this state space representation, we are going to come back when we study the state feedback controller.